Okay, so I think that now that we're familiar with the form, let's see how to go about solving with this method. This method is the reason we need to be able to write it in a factored form is we need to be able to divide and multiply things over. So the trick really lies in getting the y variable on the same side as the dy dt. So this is how this works. If all I do is I figure out a way to first of all factor out my equation, and we've already observed that one way you can do this is by writing 0.2 times y like this, calling this your g of t and calling this your h of y. So divide the h of y over, and that would give us 1 over y times dy dt equals 0.2. Now the multiplication piece, or rather division, which is multiplication by an inverse, is very, very convenient because now what I'm going to do is I'm going to integrate both sides with respect to t. And that's the only step that we needed to do in order for this to work out. Now the issue that we would have if we had just tried to integrate our starting equation is if we had just integrated both sides normally like this, and then we try to take the integral of 0.2y dt. The problem with this right-hand side is we're trying to integrate with respect to t, but the variable here is a y. So you can't integrate y with respect to t. And some Calc 3 people, if you've taken Calc 3, then you might say, well, I can use partial integration, but y is not an independent variable. Y is actually a function, and it's a function of time. So this variable is some expression involving t, we just don't know what it is. So unfortunately, you're not going to be able to integrate that. And therefore, by rearranging things like we've done here, what this does is we have division by dt and multiplication by dt, and this integral ends up being an integral with respect to y. You could also make an argument about that if you use u substitution here, then this becomes a u substitution problem, but I like to go with the method of the dt's cancel, and now on your left-hand side, observe that our integral is now with respect to y. So we're integrating 1 over y dy. We've changed the variable of integration in this way. And it was just that one simple step of dividing the y function over. Now the integral of 1 over y is the natural log of y, and it's really the natural log of the absolute value of y. That's not going to become super important for us, but it's just a good practice. Now anytime you integrate, you add an arbitrary constant. So I'm going to add a c here, and over here 0.2 is 0.2t as its integral, also plus an arbitrary constant. But wait a minute, these aren't necessarily the same arbitrary constant, because when I take the derivative of the natural log of y plus any number, I'm going to get 1 over y, and same thing for the derivative of 0.2t plus c. So I'm going to keep track of these by putting subscripts here. And now I have already solved the differential equation, because the goal of solving it is you have no derivatives left. But this is not a very useful equation, because if I want to go and graph this or do some analysis, I want to get an explicit function in terms of y. So I want to solve for y. And in order to do that, I'm going to move everything else over. The natural log of y equals 0.2t plus c2 minus c1. Now here we're going to make the claim that if you take two constants that are arbitrary and you subtract them or combine them in any way, you still have an arbitrary constant. So I don't really care specifically about the value of c2. I don't really care about the value of c1. What I really care about is the result of that difference. And I'm going to assign that to a new variable, call it c, which is still an arbitrary constant. So all I'm doing is just combining constants into one constant. And I have natural log of y equals 0.2t plus c. Now we're almost at the point of solving for y. Now we're going to exponentiate both sides. So e to the power of the left has to equal e to the power of the right. Now on the left-hand side, well, the reason we did that is because e raised to the ln, those are inverse operations and they cancel. So this leaves me with just y equals, as I've desired. And here I have to be careful because the plus c is in the exponent. You cannot just write plus c down here. You can't do that because that's violating the principle of if natural log of y equals 0.2t plus c, then by exponentiating both sides, the powers still have to be equal to each other. And if you didn't write that plus c in the exponent, then you've basically violated the equality from your last step. But here's one cool thing that we can do. One cool thing that we can do is use the property of exponents. So one thing that we know is if you take x squared times x cubed, for instance, that's equal to x to the 2 plus 3. Because x squared is x cubed is x times x times x, and you basically have 5 factors, so you would have x to the 5th. But this goes both ways, right? So if I have two bases that are common multiplied together, I can add their exponents, but if I have a base with a sum in the exponent, I can break it back up into factors. So here I have that, so I can write this as e to the 0.2t times e to the c. Just again, property of exponents. And the reason I want to do that is because here I have a constant raised to the power of an arbitrary constant. And that itself will be a brand new arbitrary constant that I'm just going to label as, well, I could relabel it as c if I want to, because ultimately we're not going to ever go back to c2 and c1, but just to differentiate it from the different constants, I'll call that k. And my final answer is y equals k e to the 0.2t. And that actually agrees with what claim I made back up here, which is that if you solve this guy, you get some arbitrary constant times e to the 0.2t. We ended up having a k there, but we could have called it c. That's kind of a weird thing to want to do, though, right? Because if I had just called this C3 and C4, some people like to keep track of them. Every time they make a substitution, they give it a new subscript value, but it's really not important. You can keep replacing arbitrary constants with the same thing. So e to the c, we could have just called c once again. I know that seems kind of counterintuitive, but if it feels better, you can always make substitutions like we've done here. Okay, so that's really how the technique works. It always works the same way. The one thing to think about, though, is some people will want to do this. And this is what a lot of tutorials will show you, is what they'll do is they will separate the dy and the dt. They'll do something like this. They'll say dy equals your function of t times your function of g. I think we've called this g of t and h of y, but the notation is not that critical. And they multiply the dt over here, and then divide the function of y to the other side, like this, and make this f of t dt. And then they're like, oh, all you have to do is just slap on that integral sign, and you're good. But there's a slight logistical problem here. And the problem is that whenever you integrate, you have to specify the variable of integration. So you can't just use existing differentials and just say, well, the left-hand side is with respect to y, the right-hand side is with respect to t. Now, ultimately, this does work, but not for the reason that we're describing here. The reason this actually works is if we follow the same logic as we did up here, what we did is we divided the g of y to the other side. Whatever function that might be, we divided it over. In our case, it was just g of y equals y. And so then we have 1 over g of y dy dt equals f of t. And now, when you go ahead and integrate that with respect to t on both sides, the dt's cancel out. And that's the step that we performed here. Now, if you don't like the cancellation method, some mathematicians will disagree with that, but really what's happening here is there's actually a u substitution that can take place that will, when you take its derivative, you get a d by dt, but I like to think of it as the dy dt's cancel, or the dt's cancel, and now I'm integrating 1 over g of y with respect to y, and I'm integrating f of t with respect to t. And you notice, hey, that gave us the same answer as we got using the wrong method. And the reason I emphasize this is because this is technically mathematically valid. What's happened here is invalid because of the fact that I did not specify a variable of integration, that I just kind of used the existing differentials there. And that's not really allowed, but it does work. So just because it works doesn't mean it's a good idea. And this is if you take this approach, you're integrating both sides and you're specifying that variable of integration. You're not going to make the same mistakes.